Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hello, it's my pleasure to welcome Stephen Wang from Stanford University. His thesis is on entity resolution, data analytics more broadly, and he's going to be talking to us about it.
All right, thanks Roga for the introduction. So I'm Stephen Huang, and I'm a PhD student at Stanford University. Today I'll be talking about my thesis work called Data Analytics, Integration, and Privacy. So nowadays, the amount of data in the world is exploding, and companies are just scrambling to make sense out of all this information. Now, there are lots of recent articles talking about analyzing large amounts of data. And here's one cover article from The Economist, cover page. You can see that there are lots of zeros and ones raining from the sky, and there's this gentleman in the middle trying to gather some of the rain, and he's watering this flower, which signifies useful information that's being extracted from all this information. So within data analytics, I've been working on two problems, data integration and data privacy. Now, even before you start analyzing data, it's very important to combine data from different sources. And so data integration plays an extremely important role in data analytics. For example, a few years ago, we had this devastating earthquake in Haiti where a lot of people died, and people around the world came as volunteers to help out the Haitians. The following figure shows different types of data that was integrated and analyzed in order to help out our Haitian friends. So first there were SMS broadcasts, and then people were texting each other, and then the local media was generating a lot of data about what was happening after the earthquake, and finally there weren't any official maps in Haiti for navigation, so people geotagged their own location and crowdsourced the maps, and these were used for volunteers to drive around Haiti. So you can see that data integration played a very important role in helping out the Haitians. Now, MSR has been a pioneer in data integration, so I really don't need to motivate this problem for this audience. So the second topic I worked on is data privacy. So the following image is from a recent Wall Street Journal article, and it's depicting how insurance companies nowadays are sifting through the web and collecting personal information and analyzing it in order to predict the lifespans of their customers. So let's say that we have Sarah on top in green color, and let's say that she has a lot of bad health indicators. For example, she has good health indicators. If, for instance, she only has 1 mile of commute distance, and let's say she does a lot of exercise, and then she reads a lot of travel magazines, and she does not watch much television. On the other hand, let's say that we have Beth on the bottom in red color, and this time let's say she has a lot of bad health indicators. So for example, here she has a long commute distance of 45 miles, she buys a lot of fast food, and she has bad foreclosure activities, and she watches a lot of TV. All this type of information can be found from social networks, blogs, and homepages. And in this example, the insurance company may conclude that Beth is likely to be, is probably less healthier than Sarah, and therefore is more likely to have a shorter lifespan than Sarah. Now, although this kind of analytics may be very useful for the insurance companies, it's very disturbing for the customer side. And there's actually a study that shows that there's a high correlation between the analysis of this data with the actual medical tests that the insurance companies perform on their patients. So so I've been studying the problem of data analytics in the data privacy point of view as well. And there's an interesting connection between data integration and data privacy. So the better you are at integrating data, the more likely someone's information is leaked to the public. So you have worse privacy. And vice versa. The better privacy measures you take, the harder it is to integrate information. So it's no coincidence that I've been studying these two problems. So the following slide summarizes my PhD work. First, I've written a number of papers on a topic called entity resolution, which is a data integration problem. Second, I've recently written a number of papers on data privacy. And finally, I've published a paper called Indexing Boolean Expressions, which was done while I was interning at Yahoo Research. And the techniques here were used in the display advertisement prototype of the Yahoo web page. So for this talk, I'm going to focus on the following works. During part 1, I will elaborate on a work called Evolving Rules. And during part 2, which is going to be shorter than part 1, I will mainly talk about a work called Managing Information Leakage and briefly talk about a newer work called Disinformation Techniques for Entity Resolution. So entity resolution is a problem where you want to identify which records in a database refer to the same real-world entity. For example, you might have a list of customers where some of these records refer to the same person, and you might want to remove the duplicates efficiently. Now, entity resolution can be a very challenging problem. So in general, you're not simply given IDs like social security numbers that you can just compare. Instead, many records contain different types of information, and other records may have incorrect information like typos, which makes entity resolution an extremely challenging problem. There are many applications for entity resolution. So in our Haiti example, you can think of the scenario where there are lots of people sick in bed, so the hospitals might have these lists of patients. At the same time, other people may be posting photos of loved ones that are missing. So now you have an entity resolution problem where you want to identify which patients in these hospital lists refer to the same people as those in these photos of missing ones. In addition, there are many other applications for entity resolution, and this makes entity resolution an extremely important problem as well. So to summarize my research focus, I'm not trying to solve the entire data analytics problem. This is a huge problem that requires a lot of research to completely solve. Instead, I'm focusing on a sub-problem called data integration. Within that, I'm solving an entity resolution problem. And for this presentation, I will focus on scalability. So my work on evolving rules was motivated through my interactions with a company called Spock.com. So this is a people search engine that collects information from various social networks like Facebook and MySpace, blogs, and Wikipedia. And the goal is to resolve hundreds of millions of records to create one profile per person. Now, whenever I was going to Spock, I was hearing all of these discussions of how to improve the logic comparison rule for comparing people records. At one point, they were talking about comparing the names, addresses, and zip codes of people. But when I made another visit, they realized that the zip code attribute is not a good attribute for comparing people. So they then decided to compare the names, addresses, and phone numbers of people. So every time I made a visit, they were always making these incremental changes of their comparison rule. And that made me think of how to produce an updated ER result if you change your comparison rule. So let's say that starting from an input set of records I, we use a comparison rule to run entity resolution and produce a resolved set of records. Now, if you change your comparison rule, then the naive approach is to simply start from scratch and produce a new result using the new comparison rule. Now, the naive approach obviously produces a correct result, but it's not necessarily the most efficient result. And if you're a company like Spock.com that's resolving hundreds of millions of records, then you really don't want to start from scratch every time you make a small incremental change on your comparison rule. So in our paper, we propose a technique, incremental technique that can basically convert an old ER result into a new ER result. And we call this process rule evolution. And hopefully, rule evolution is much more efficient than simply starting from scratch. So for example, let's say that we want to resolve 4 records. Yes, please.
It's a very expensive operation to go through and run the rules again. I'm trying to understand the motivation for trying to reduce the computation.
Right. So I'm going to illustrate that problem. Well, I'm going to show our solutions using this simple example. So bear with me. So for example, let's say that we're trying to resolve R1 through R4, and each record contains the attributes name, zip code, and phone number. Now, of course, in the real world, there may be many more attributes and many more records to resolve, but I'm only showing you a small example for illustration purposes. Now, let's say that we use a simple ER algorithm where we first perform pairwise comparisons of all the records, and later on, cluster the records that match with each other together. So initially, let's say that our comparison rule compares the names and zip codes of people. And if two records have the same name and zip code, the comparison rule returns true and false otherwise. So in this example, the only matching pair of records is R1 and R2 because they have the same name John and the same zip code 54321. And there are no other matching pairs of records. So after clustering the matching records, we get our first ER result, where R1 and R2 are in the same cluster, but R3 and R4 are in separate clusters. And the total amount of work we performed here is 6 pairwise comparisons, because we were comparing 4 records in a pairwise fashion. Now notice that record R4 has a null value for its zip code. So this may be an indicator that the zip code attribute is not an appropriate attribute for comparison because it seems to be very sparse. So let's say that we now change our comparison rule and compare the names and phone numbers of people instead of the names and zip codes. So using the naive approach, again, we're going to compare all the records in a pairwise fashion. And in this case, the only matching pair of records is R2 and R3 because they have the same name John and the same phone number 987. So after clustering the records that match with each other, we get our new ER result where R2 and R3 are in the same cluster and R1 and R4 are in separate clusters. And the total amount of work we've done here is, again, 6 pairwise record comparisons because we've started from scratch. Yes, please.
So why are you saying that we'll look from such comparisons? Wouldn't the number of comparisons be a function of the key that you're using for every case? Wouldn't the number of comparisons you're doing for each case be a function of which fields you're using, of which rule you're using? You're saying you're always doing pairwise, but it seems like you know what the rules are. So the number of comparisons would be a function of what the rule matches.
Right, so here I'm using a simple ER algorithm that just blindly does pairwise comparisons, but you can think of more advanced ER algorithms that kind of reduce the number of the record comparisons as well. I'm illustrating using a simple ER algorithm, and it always performs pairwise comparisons among all the records. That's why I'm just saying it's 6 comparisons. If you use a different ER algorithm, then you can get a case where it does fewer than 6 comparisons. But just bear with me because this is, I'm not saying that this is the state-of-the-art ER algorithm at all. So now, while 6 comparisons here may not seem like a big deal, if you're resolving hundreds of millions of records, then this is a big deal. So we would like to reduce this number as much as possible. So before I give you the answer of how to efficiently produce the name and phone number results, let me go through an easier example where I would like to perform rule evolution from name and zip code to name and zip code and phone number. So in this case, there is an interesting relationship between the 2 comparison rules. The second comparison rule seems to be stricter than the first comparison rule. And you can see that 2 records that do not match according to name and phone number will not match according to name and phone number and zip code as well. So therefore, notice that we don't have to, starting from the first result, we don't have to compare the records across different clusters because we know they will never match according to the new comparison rule. Instead, we only need to compare the records within the same cluster. So in this case, we'll only compare R1 and R2. And it turns out that R1 and R2 have different phone numbers, so they end up in different clusters. So just by performing one record comparison, we've produced our new ER result for name and zip code and phone number, which is much more efficient than the 6 record comparisons that would have been produced using the naive approach. Yes, Raghav?
So for this example to hold it in Europe, you're assuming that the rules such as Boolean combinations.
Right. So I'm assuming that the comparison rule is in a conjunctive normal form of arbitrary predicates in general.
People propose models where it's like weighted combinations and there are other ways of combining the evidence, right?
Right. So later on, I also have these rule evolution techniques for distance-based clustering ER algorithms where you're clustering records based on their relative distances. So I'll talk about that later on. So going back to our original problem, notice that you can't use the exact same technique used here to produce the name and phone number result because there's no special strictness relationship between name and zip code and name and phone number. So for example, although R2 and R3 are in different clusters in the first result, they might have the same name, and if they also have the same phone number, then they might result in the same end up in the same cluster in the name and phone number result. So we can't use this technique, and our solution for this problem is to use what we call materialization. So in addition to producing the ER result for name and zip code, the idea is to produce an ER result for the name comparison rule and another result for the zip code comparison rule as well. And starting from this materialization, notice that we can exploit the name result to efficiently produce the name and phone number result using the exact same technique used in the previous slide. So again, there's this interesting strictness relationship where name and phone number is stricter than name. So we're only going to compare the records that are within the same cluster in the name result. And only just by doing 3 pairwise record comparisons, we can now produce the name and phone number result, which is much more efficient than the 6 record comparisons that would have been produced by the naive approach. So here, rule evolution seems to be very efficient, but an immediate question you can ask is, what are the costs we pay for doing this, using this technique? So there are time and space overheads for creating these materializations. In this example, it seems like we're running anti-resolution 3 times, which basically defeats the purpose of reducing runtime. So in our paper, for the time overhead, we have various amortization techniques, where the idea is to share expensive operations as much as possible when we're producing multiple ER results. For example, when you're initializing the records, you have to read the records from the disk, and you have to parse them and do some more processing. And this only needs to be done once, even if you're producing ER results multiple times. We also have ER algorithm-specific amortization techniques. So one of the ER algorithms we implemented in our work always sorted the records before doing any resolution. And the sorting here was the bottleneck of the entire ER operation. So in this case, we only need to sort the records once, even when we're producing ER results multiple times. So all of these amortization techniques combined, it turns out that the time overhead is reasonable in practice, and I'll show you some experimental results later on. Now, for the space overhead, notice that we need to store more partitions of the records. But the space complexity of storing partitions is linear to the number of records. And in addition, we can use compression techniques where we only can simply store the record IDs in partitions instead of copying the entire contents of the records over and over again. So again, in our paper, we show that the space overhead of materialization is reasonable as well. So we've considered many different, yes, Arvind?
How do you know what to materialize?
Oh, yeah, so in general, we view the comparison rule as a conjunctive normal form, and the strategy is to materialize on each of the conjuncts. Now, this is the most general case because we don't know how the new comparison rule is going to change, but you can actually improve this approach by if you know some more information. For example, if some of the conjuncts always go together, then you don't have to materialize on each of the conjuncts. But in this, the most general approach, we materialize on one conjunct at a time. Yes, please.
What you're describing is not specific to ER at all. We can talk about a relational query processor which is evaluating a selection of a collection of conjuncts, and I want to materialize some of the intermediate results for future use, right?
Yes.
So how does your technique compare against? Because people have done that kind of work, right? They're talking about materializing intermediate results. How does your technique compare?
Yeah, there's a great deal of work on materialized views. This is in the same spirit as materialized views, but this is mainly I'm working on clusters of records. So this is more this is an ER algorithm, the ER specific technique. So I'll just keep on explaining, and hopefully this will be clear. So I've considered many different ER algorithms in the literature, and we've categorized them according to desirable properties that they satisfy. So if an ER algorithm satisfies one or more of these properties, then we have efficient rule evolution techniques. So the first property we identified is called rule monotonicity. And here you can see a number of ER algorithms in the literature that satisfy this property in the red circle. The second property is called context-free, and you can see, again, a number of ER algorithms in the literature that satisfy this property in the blue circle. And in addition, we used two other properties in the literature and further categorized the ER algorithms according to the properties they satisfy. And depending on where you are in this Venn diagram, we have different rule evolution techniques that you can use. In this talk, I will only focus on the purple area, which is the intersection of rule monotonicity and context-free. So I'll define these two properties and then explain, illustrate our rule evolution technique. But before that, let me define two preliminary notations. Yes, please.
So a lot of the real systems, they will decouple the AR process into stages, such as blocking, pairwise comparison, clustering, and so on. Does this characterization then spread to the individual components of this pipeline, or it only applies to systems which are described as a single stage?
Yeah, here I'm assuming all the steps to be one ER algorithm. So we assume that an ER algorithm basically receives a set of records and returns a partition of records. So this can include blocking and resolution and post-processing. So everything is included in this black box ER algorithm.
Do you think you could extend this to individual stages, given that systems tend to be more piecemeal, where they want to plug in some blockers, then they want to play with some clusters and so on?
Yeah, certainly. So you can view blocking to be a separate process from NC resolution. So it's kind of an orthogonal issue. So in order to scale NC resolution, you can use blocking separately. But for when you're resolving each of the blocks, you can use the rule evolution techniques here. Yeah. Okay, so a comparison rule B1 is said to be stricter than B2 if for all the pairs of records that match according to B1, they also match according to B2. For example, name and zip code is stricter than name because any two records that have the same name and zip code will also have the same name as well. Now, the second preliminary notation is domination. So, so an ER result is dominated by another result if for all the records that are in the same cluster in the first result, they are also in the same cluster in the second result as well. So in this example, if you look at the first ER result, the only records that are in the same cluster are R1 and R2. And since these two records are in the same cluster in the second ER result as well, the first ER result is dominated by the second ER result. But this third ER result is not dominated by the second result because although R3 and R4 are in the same cluster, they're not in the same cluster in the second result. So this is not dominated. So using the strictness and domination, I can now define the rule monotonicity property, which is defined as follows. It's saying that if a comparison rule B1 is stricter than B2, then the ER result produced by B1 must always be dominated by the ER result produced by B2. So for example, let's say that we're producing an ER result using the name and zip code comparison rule, and we produce another ER result using the name comparison rule. Then if the ER algorithm satisfies rule monotonicity, it must be the case that the first ER result is dominated by the second ER result. So the second property is called context-free, and the formal definition is shown on the screen. Intuitively, it's saying that if we can divide all the records into two sets, such that we know that none of the records in these two different sets will ever end up in the same cluster, then we can resolve each data set independently. So for example, let's say that we have 4 records, R1 through R4. And let's say that R1 and R2 refer to children, while R3 and R4 refer to adults. So from the start, we know that none of the children will ever end up in the same cluster as with the adults. So we can divide the records into the following 2 sets. So if the ER algorithm satisfies context-free, then we're allowed to do the following, where we resolve each set independently. So we can first resolve R1 and R2 together without caring whatever happens to R3 and R4 and produce clusters. Then we can resolve R3 and R4 without caring whatever happens to R1 and R2 and produce another set of clusters. And the property guarantees that by simply collecting the resulting clusters, we're guaranteed to have a correct ER result. Now notice that I have this cute diagram of a thick black wall in the middle, which is basically stopping information from flowing to the left, from left to right, or from right to left. Yes, please.
It's like B is a set of rules.
B is the rule, yes. Yes. Right, so as an example where context-free is violated, let's say that R3 is the father of R1 and R4 is the father of R2. let's say that the ER algorithm first compares R1 and R2 and clusters them together, and compares R3 and R4 and puts them in separate clusters. Now, the fact that R1 and R2 are the same child may be strong evidence that R3 and R4 are actually the same father. So the ER algorithm may change its mind and end up merging R3 with R4. So that's an example where some information is flowing from left to right. So that's a violation of this context-free property. So using rule monotonicity and context-free, I'll illustrate a rule evolution algorithm that exploits these properties to do efficient evolution. So let's say that we are evolving from the comparison rule name, address, and zip code to name, address, and phone number. Now, first of all, I'm going to materialize on all the conjuncts. So in this example, I will produce an ER result for the name comparison rule, and another result for the address result, and another one for the zip code result. But I don't show the zip code result due to space constraints. So during step 1, the algorithm is going to first identify the common conjuncts of the old and new comparison rules. In this example, the common conjuncts are the name and address comparison rules. And it's going to perform what we call a meet operation between among the ER results of the common conjuncts. In this example, we're going to perform a meet operation between the name result and the address result. Intuitively, we're taking the intersecting clusters. So in this meet result, you can see that R2 and R3 are in the same cluster. And the reason is that these two records are in the same cluster in the name result, and they're also in the same cluster in the second result as well. But R1 and R2 are not in the same cluster in the meet result because although they are in the same cluster in the name result, they are not in the same cluster in the address result. Now, using rule monotonicity, we can prove that this meet result always dominates the final ER result, which means that none of the records in different clusters are ever going to end up in the same cluster in the end result. So during step 2, the algorithm exploits the context-free property, and since it knows that none of the records can match across different clusters, it's going to resolve each cluster independently. So for the first cluster, it only contains R1, so we're going to return R1 as a singleton cluster. For the second cluster, we're going to compare R2 and R3, and let's say that it turns out R2 and R3 are refer to different entities, so they are placed in separate clusters. Finally, for the third cluster, it only contains R4, so we return R4 as a singleton cluster. And simply by collecting the final clusters, we're guaranteed to have arrived at a correct ER result. And the total amount of work we've done here was only one record comparison, which is much better than the 6 record comparisons that would have been performed by the naive approach. So in summary, I've defined the rule monotonicity and context-free properties, and I've illustrated an efficient rule evolution algorithm that works well for this purple area. Again, depending on where you are in this Venn diagram, we have different rule evolutions that work for those regions as well. Yes?
The ideas that you mentioned in the example, it actually relied on the fact that you were doing equality on name and address, right? So suppose my conjuncts were of the form like name similarity larger than 0.9 or name similarity larger than 0.8. It's possible that when you are actually evolving the rules, the constants, the thresholds on each of the columns actually get changed.
Right.
In which case, like materialization becomes much more tricky, right?
Yeah. So I'm assuming that the conjunction rule is a conjunctive normal form of arbitrary predicates. So within the predicate, you can use whatever similarity function you like. Here, I was just showing you an easy example where we only perform equality constraints. So
I'm not questioning that the approach, the correctness is obvious if you kind of materialize on each other predicates.
Right.
Like when you have such constants in thresholds, it's not like you have to materialize many more predicates, right? So if you have name larger than 0.9, like which predicate will you materialize?
Yeah. So in this model, if you're doing a similarity comparison between names and you're comparing with a high threshold, and you have another predicate that uses a lower threshold, we consider these two predicates to be totally different. Right. So that's but you can do more optimizations by taking into account that these two predicates are actually doing the same string comparison compared with the title with the threshold. Yes.
What if you evolve the rule by changing the threshold, not by adding conjunct?
Yeah. So it depends on the ER algorithm. If you are using, for example, the single link hierarchical clustering, and you relax you relax the threshold, which means you reduce the threshold, then all you have to do is build on top of the previous ER result. Now, if you go the other way around, then this approach does not work. Yeah. Yes, Vivek.
So you talked about changing the rules, right? What about if the data changes? Then does the materialization still work?
Yeah, so that's a very important problem. This work is mainly focused on when the comparison rule itself changes. So it's an orthogonal problem, and in the future I'd like to do research in both directions. But this work does not consider the case where you're having a new stream of records which you'd like to add to your ER result. Okay, so far I've been talking about rule evolution techniques for what we call match-based clustering algorithms. In our paper, we also have rule evolution techniques for what we call distance-based clustering algorithms. So here, records are clustered based on their relative distances. So I won't have enough time to go through all the details, but just to give you the high-level idea, let's say that we have 4 records, R, S, T, and U. And let's say that the record S is close to R because S is within that dotted circle around R, but the records T and U are far away from R because they're outside that dotted circle. Now, whenever the distance function changes, all these pairwise distances are going to change as well. And although we don't know how exactly those distances will change, let's say we at least know the lower and upper bounds of those distances, as denoted as the red brackets. So for example, the record S may suddenly become closer to R, or it may end up further away from R, but we still know that S will still be inside that dotted circle. So we know that S is will still be close to R. And for record U, although the distance from R is going to change, we still know that U is going to be outside that dotted circle. Now, the interesting case is record T. So T may end up within that dotted circle or outside the circle. And in that case, we're going to be optimistic and cluster R and T together, but later on revisit this cluster and check if R and T are indeed close with each other. If not, we're going to split T out of R's cluster. So I'm glossing over a lot of details, but that's the high-level idea for rule evolution for distance-based clustering algorithms. So the following slide shows all the data sets I've been using for all my ER works. The first data set is contains shopping items provided by Yahoo Shopping, where items were collected from different online shopping malls. And each item represents a record represents an item and contains attributes including the title, price, and category. Now, since these records were collected from different data sources, there are naturally many duplicates that need to be resolved. The second data set is a hotel data set provided by Yahoo Travel. And again, records were collected from different travel sites like Orbitz and Expedia. And again, different records may refer to the same hotel. And while there aren't too many records here, there are many attributes per record. So the data is very rich here. Finally, we have a person data set provided by Spock.com, where people records are collected from social networks like Facebook and MySpace, and blogs and Wikipedia. And we have a lot of records here. And each record contains the name, gender, state, school, and job information about a person. So among these 3 data sets, for my evolving rules work, I only performed experiments on the shopping and hotel data sets. And in this talk, I'll only show you experimental results using the shopping data set. Yes, Ravi?
For the data sets of these size, how expensive is it to run the naive approach?
Oh, does it take hours? Extremely expensive. Yeah, you don't want to run the naive approach. Well. Okay, so the naive approach is defined to be starting from scratch, right? Okay, so your question is, how fast how long does it take to resolve hundreds of millions of records? Yeah, so I was interacting with Spock.com, and I think it takes in the order of hours or maybe days. But I'm not sure about the exact number because it's kind of it's kind of a secret that they have, so they weren't revealing all the numbers to me.
An MapReduce system to do this? Or?
Not that I've known, not Spock.com. So this company recently got acquired by a company called Intellius.com. So since then they might have changed their strategy. But when I was interacting with Spock.com, they were just using a regular DBMS like MySQL. Yeah. Yes, please.
Can you comment on the gold standard sets for each of these?
Yeah. Good questions. For the hotel data set, we had a gold standard, which was provided by a Yahoo employee that we knew. But for the other two data sets, we don't have a gold standard. It's very hard to generate a gold standard for these data sets. So I'm going to show you two representative experimental results of my work. And both of them are going to be runtime experiments. The reason I'm not going to show you any accuracy experiments is that our techniques are guaranteed to return 100% accurate ER results all the time. So we're not trading off accuracy with scalability. We're only improving the scalability of rule evolution. So that's a feature of our work. So this plot shows results of evaluating our techniques on 3,000 shopping records. And the x-axis shows the strictness of the common comparison rule. So we tested on many different comparison rules. And in some of these experiments, we evolved from title and category to title and price. Now, in that example, the common comparison rule is the title comparison rule. And for this rule, we were extracting the title from two different records, and we were computing the string similarity of the two titles. And we then compared this value with the threshold. Now, if we increase the threshold, then the title comparison rule becomes stricter in a sense that fewer records match according to their titles. So in that case, we move to the left side of the x-axis. On the other hand, if we decrease the threshold, then the title comparison rule becomes less strict in a sense that more records match with each other. So in that case, we move to the right-hand side of the x-axis. So just think of the x-axis to represent different application semantics. Now, the y-axis shows the runtime improvement of rule evolution versus the naive approach. But here, I did not include the time overhead for materialization. But in the next plot, I will compare the total runtime of rule evolution, including the time overhead, with that of the naive approach. So I implemented 4 different ER algorithms in the literature. And you can see that in the best case, we get over 3 orders of magnitude of improvement, while even in the worst case, we still improve the runtime improve the naive approach. Yes, please. The naive approach is to simply run ER from scratch without exploiting the materialization. So, given a set of records, simply run your own ER algorithm using the new comparison rule. So these are the 4 different ER algorithms. The red plot is the sorted neighbor technique, where we sort records and then we use a sliding window and compare the records within the same window. These are all different techniques. HCB means that we're merging records that match with each other in a greedy fashion. And HCBR is similar, but we have some properties, desirable properties, that guarantee that the ER result is going to be unique. And finally, HCDS is a distance-based clustering algorithm. It's the single link hierarchical clustering algorithm.
Have you tried other clustering K-means, like similarity joins, K-means?
Right. So K-means did not satisfy any of the properties, so it was not like a good ER algorithm to demonstrate our techniques. Yeah. So when you're comparing the total runtimes, here's what you should expect. So let's say that for rule evolution, you're performing materialization once, and then you perform rule evolution 1 or more times. So the x-axis here shows the number of evolutions, and the y-axis shows the total runtime. Initially, for rule evolution, we're paying an overhead for the materialization. So rule evolution is slower than the naive approach. But as we perform more rule evolutions, the incremental cost paid by rule evolution is smaller than the cost for the naive approach, where we simply run ER from scratch. So at some point, you can imagine rule evolution is going to outperform the naive approach. Now, the following slide shows a result of one scenario we've considered. The x-axis shows a number of shopping records that were resolved, and the y-axis shows the total runtime in hours on a log scale. I'm only going to explain the top 2 plots that are colored. So the red plot shows the total runtime of the naive approach, while the blue plot shows the total runtime of when we're using rule evolution using the exact same ER algorithm. And here we performed materialization once, followed by one rule evolution. And you can see that the blue plot still improves the red plot, which means that in this case, the rule evolution was saving enough time to compensate for the time overhead paid by time overhead for materialization. And although this gap seems very small, the unit of the y-axis is in hours, so the gap is actually, the runtime improvement is actually significant. Now, yes, it's also a log scale as well, so that makes it the improvement even more significant. Now, the important thing to understand here is that this result shows is only for one scenario we've considered. You can think of many other scenarios where you can either get results that are much better than these results or much worse. For example, if you're comparing multiple evolutions instead of just one, then you're probably going to have much better runtime improvements than those shown in this plot. On the other hand, you can think of pathological cases as well, pathetic cases. So, for example, if the old and new comparison rules are totally different, then there's no point in performing rule evolution because there's nothing to exploit. So in this case, just simply running the naive approach is the most efficient technique. And if you run rule evolution here, you're probably slower than the naive approach because you still have to pay the time overhead for materialization. So the takeaway of this plot is that we now have this general framework for rule evolution that you can use to evaluate if rule evolution makes sense to your application or not. So in conclusion, we proposed a rule evolution framework that exploits ER properties in materialization, and we've shown that the rule evolution can significantly enhance the runtime of the naive approach. So that was the first part of my talk, and the second part will be much shorter. Yes, but
you thought about rules that are linear combinations of predicates, that are weighted combinations.
Linear combinations. So I think that's the case of distance-based clustering. So an example for a distance function is you add the titles, the name similarity with the address similarity, and you can do a weighted sum. So at the end, you get some distance value. So our distance-based rule evolution techniques for distance-based clustering algorithms work for your case.
In the non-metric case, in the case where it's a nonlinear sum, or if the distance is not in the metric space?
As long as you return a distance, it's fine. So you don't have to satisfy any triangular property or anything. But the only assumption we make is that you have to have an idea of how much this distance can change in the next evolution. So we have to have some information that, for example, each distance is only going to change at most by 10%, or by some constant amount like 5. So as long as we have that information, you can use our techniques. Yep.
So what about disjunctions? Decision trees of rules.
Right. So in this work, we assume conjunctive normal form. So if you only have disjuncts, then everything is going to be considered as one predicate.
Not only disjuncts. It's a decision tree, so you have conjunction and disjunction.
Okay, so we assume that you can convert this into a conjunctive normal form, and then the idea is to materialize on each of the conjuncts. Yeah. Yes, please.
This is overhead materialization.
Yeah, so I mentioned that briefly. So so we're only saving multiple partitions of records. Now, instead of so the space complexity is linear to the number of records, but notice that you can use a lot of compression techniques. So you can save a partition of record IDs instead of a partition of the actual records. So this saves a lot of space, and it turns out that the space overhead is reasonable in practice. It doesn't, yeah, it's not more than 10%, basically.
Could it happen that you lose your advantage in normalizing the query, or in normalizing essentially the rules to conjunctive normal form? So there might be blowups there.
Yeah. So that's an issue. That's I guess that's a concern that we have.
Are most rules already in nice form, or?
Well, so we're.
Do valid assumptions to assume that there's no blowups there?
So at least for the experiments we performed, a lot of these comparison rules were just conjunctions of predicates. So we believe that this is it's reasonable to assume that you have a conjunction of predicates. Yeah. But there is definitely the complexity for converting a DNF expression to a CNF expression is exponential. But this is, but once you do that, then you can use our rule evolution techniques. Yes, please.
So, your speed up is a function of the kind of the sequence. It's a function of the sequence of rules that you have, and empirically, what do you find in terms of the rule sequences that you see people using for energy resolution?
Yeah, so my understanding is that I don't have well, again, I've interacted with Spock.com, but they didn't give me all the details they have. But my impression is that some of these predicates are always used. So you always compare the names and addresses of people. And afterwards, you may compare the zip codes or phone numbers or some other attribute, like well, gender, for example. So in that case, you can actually do something better than, you can improve this approach where you can materialize on the name and address combination. And if you have a zip code, then you may or may not materialize on the zip code. So this is a very application-specific optimization. You have to see which conjuncts are used together and which conjuncts will likely to change or not. And my understanding is that certain conjuncts never really change. It's only kind of like the tail that's changing. But I can't confirm that.
One other follow-up question is, how many iterations would someone typically go through in trying to resolve or create an energy resolution system?
So when I was visiting Spock.com, every time I made a visit, they were discussing how to improve their comparison rule. So this always happens. I can't give a definite number, but it's always a continuous improvement. So it's very rare that you have complete information about your understanding about your data and applications. So in the real world, you're always getting more while you're constructing your system, you're getting a deeper understanding of your application, and you make improvements to your match function and comparison rule, and then it's a back and forth thing. So then you evaluate this rule, and then you realize you've missed something, and then you improve your comparison rule, and this kind of repeats. So it's pretty frequent. Yes, please.
So this goes back to some questions about the scalability of the naive algorithm. In some sense, they may not be that naive with respect to scalability. Right? For example, if you look at many of the ER techniques, you can say there's two parts. There's a sort of a pairwise matching, detecting things that are likely to match, and then there's sort of the clustering step. Right? Both of these, if I'm not mistaken, can be very nicely parallelized. Right? So in your implementation, did you sort of compare against a well-designed ER as your baseline, or what did you have? What was used? What techniques were used to sort of make? So with respect to such a system, then how much benefit do you still see?
Right. So for my work, I only considered the ER algorithms in this Venn diagram. So I know these are very cryptic, but this is sort of the sorted neighbor technique, and this is the HCs are all hierarchical clustering. The ME is the technique proposed by Monge and Elkan, where you have a queue and you want to only compare each new record with clusters in the queue. So Raghav was mentioning k-means, but we didn't consider k-means, and we didn't consider your case where you have this very scalable way of decoupling the identification of candidates followed by clustering. So these are the algorithms we use in our paper. But it'd be very interesting to actually see how your techniques, if your algorithm actually satisfies any of these properties. Okay. Yes.
How do you pick the rule evaluation for an experiment? So was it like?
It was just handpicked. So I was just considering a comparison rule that I used contained two predicates, and then I was changing one of them. So I wasn't considering I wasn't doing entire survey of doing rule evolution. So, but this was I was just trying to demonstrate that how rule evolution saves time and compensates for the materialization overhead. But I agree. Well, there's a lot of future work that can be done from here. Basically, there are lots of unanswered questions. Okay, so I'll move on to the second part of my talk, where I will mainly talk about a work called Managing Information Leakage, and then briefly mention more recent work called Disinformation Techniques for ER. So at the beginning of my talk, I motivated you about the data privacy problem by explaining how insurance companies are sifting through the web and collecting and analyzing your personal information to predict your lifespans. Here's another interesting example for my work. So Quora.com is a Q&A site where people can ask questions and other people can answer those questions. And not too long ago, there was this person who posted a question basically challenging anyone out there to find all his information on the web. And if you look at this question, you can see there's no indicator of the identity. There's no clue about the identity of the person who asked the question. You can't find his name. There's no ID of the person who posted this question. So just by looking at this text, you can't get any clue. Now, it turns out that once you post a question on Quora.com, you become the only follower of your own question. So there was this anonymous user that came along, and he was lucky enough to see that discover like the only follower of this question. And so he clicked on the profile, got the name, and started searching through various social networks, blogs, and homepages, and to extract all the information about this guy. And so the anonymous user posted 26 bullet points of personal information about this person. One bullet point says that you're 24 and you will be turning 25 very soon. Another bullet point says that your mother's maiden name starts with the letter P. Another one says that you can program in C++. Another one says that you're related to some incident in LA back in 2009. And finally, another one says that you are a Democrat. Okay, so Joseph, who was very impressed, who turns out to be the person who posted this question, was impressed and actually categorized the 26 bullet points as follows. So some of them were categorized as correct and downright scary. So apparently Joseph did not anticipate that someone would figure out his exact age. And if someone figures out my mother's maiden name, I would be freaked out as well. Now, some of the bullet points were categorized as deliberately public. So the claim that Joseph can program in C++ was probably information that could be found in his online resume. Interestingly, there were 6 incorrect bullet points. So the claim that Joseph is somehow related to this incident back in LA in 2009 turns out to be false information. So Joseph had this Facebook profile image that was related to that incident, but it turns out this image was a deliberate obfuscation that Joseph made in order to confuse the adversary, any adversary that wanted to find his information. Also, the claim that Joseph is a Democrat turns out to be wrong as well. So in this case, the anonymous user confused this Joseph to be the same person as some other Joseph with the same name. And since this other Joseph was clearly a Democrat, the anonymous user thought that the first Joseph was a Democrat as well. But here Joseph clarifies that no party can handle his idiosyncrasies. So after this experiment, Joseph concludes as follows in bold font. He's saying that it seems to be far more effective to allow incorrect information to propagate than to try and stem the tide. So my research in data privacy is twofold. First, I like to quantify just how much of your personal information is being leaked into the public. And second, I like to propose management techniques for information leakage. Now, the interesting connection between this work and my previous works on entity resolution is that I'm assuming that the adversary is performing entity resolution to piece together information. In this example, the anonymous user was piecing together Joseph's information to know more about him. So I'm basically using the ER models I developed in my previous works to simulate the adversary to then quantify information leakage. So that's the interesting connection between this work and my previous ER works. So to formalize this problem a bit further, I'm going to assume that all the pieces of information on the web are simply records in a database, as shown as the blue boxes. And I'm going to assume that there is a notion of full information of Joseph, as shown on the top of the screen. Again, the adversary is going to perform entity resolution and piece together the relevant records that refer to Joseph. And intuitively, the information leakage is defined as the similarity of this blob of information with that complete information. So I won't have enough time to go through all the details of my measure, but here are the key features. So first, we incorporate entity resolution. Second, we don't assume that privacy is an all or nothing concept. So if you look at many previous privacy works, many of them assume that, especially in data publishing, the assumption is that you somehow have complete control of your data before you release it. So once you make it perfectly private, then you're allowed to, you can just give it to someone else. For example, A hospital may be trying to release a set of medical records of its patients to the public for research reasons. Now, there are lots of anonymization techniques you can use to make it very hard to figure out which patient has which disease. So once you've made the data entirely anonymous, then you're allowed to publish this information to the public. In comparison, our works make a fundamentally different assumption, where we assume that some of our information is already in the public. So whenever you want to interact with your friends through Facebook, you have to give out some of your personal information, like your birthday. If you want to buy a product from Amazon.com, you have to give out your credit card information. So in order to do our everyday lives, we're continuously exposing ourselves to the public. So our view of privacy is that there's no such thing as perfect privacy, and that privacy should be within a continuum from 0 to 1, and we're just trying to be as private as possible. In addition, our information leakage measure incorporates the uncertainty that the adversary has on his data and the correctness of the information data itself. So once you release your information to the public, we assume that it's very hard to delete that information. So even if you attempt to remove some information, some other people may have made copies of that information, and companies may have backup files of that information. So if you delete a photo from Facebook, who knows that if that photo is still floating around the web. So in that setting, the only way to reduce information leakage is to add what we call disinformation records, as shown in red, where the idea is to dilute information by producing records that are realistic but incorrect. Now, disinformation is not a technique that we're proposing as a new idea. This strategy has been used since the dawn of mankind. So during World War II, the Allied forces generated a great deal of disinformation to trick the Germans into thinking that they would land on Calais, but they actually landed on Normandy, and this was a main turning point of the war. So we're adapting this ancient strategy to the realm of information management. So in our paper, we propose two types of disinformation records. The first type is called self-disinformation, where the disinformation record snaps onto one of the correct records and lowers the information leakage by itself. The second type of disinformation is called linkage disinformation. And here, the disinformation record is connecting an existing record that's not correct to one of the correct records. And here, the contents of the existing record, YYY, is being used to lower the information leakage. These two strategies turned out to be very effective in practice, and we already saw examples for both of these strategies in our Quora example. Recall that the anonymous user mistakenly thought that Joseph was related to some incident back in LA in 2009. And it turns out to be, that turned out to be incorrect because the Facebook profile image of Joseph was kind of a deliberate obfuscation. That's an example for self-disinformation. The anonymous user also mistakenly thought that some other Joseph was the same person as this Joseph, and mistakenly thought that the original Joseph was a Democrat. That's an example of linkage disinformation. And in our paper, we discussed these two strategies in more detail. Now, in a more recent paper I have, which I submitted to VLDB, I focused on the linkage disinformation problem in more depth. So here I assume that the adversary is running entity resolution to cluster records that refer to the same entity. And once we have that, I assume that for each pair of the clusters, there is a way to generate disinformation that will trick the adversary into thinking that these two clusters refer to the same entity and therefore should be merged with each other. So I call that cost the cost for generating that disinformation is what we call the merge cost, and the costs are written in black numbers for each pair of clusters. Now, for each cluster that we successfully merge with our target cluster, which is Joseph's cluster in this example, we assume that there is a benefit we obtain because we're diluting the information of Joseph, which is a good thing. So for each of the clusters, I indicate the benefit in using red numbers. So given this setting, we can now formulate an optimization problem where the goal is to merge clusters in a pairwise fashion, starting from Joseph's cluster, so that we obtain the maximum benefit while paying a total cost that's within a budget B. In this example, if the budget B is 3, then the optimal disinformation plan turns out to be that green tree, where we first merge the left cluster with the top cluster and simultaneously merge the left cluster with the bottom cluster. And in that case, the total merge cost is 1 plus 2, which is exactly 3 here. And the total benefit we obtain is 1 plus 1, which is equal to 2. Now, I won't have enough time to go into all the details of our algorithms, but it turns out this problem is strongly NP-hard, which means that you can't come up with a pseudo-polynomial algorithm, and there are no approximation algorithms as well. So in the most general case, we only have heuristics. However, if we restrict the height of the plans to be at most 1, where we can only merge clusters to the target record directly, then this problem becomes weakly NP-hard, and we do have an exact pseudo-polynomial algorithm and a 2-approximate algorithm. And I'll be happy to talk about more details if you're interested. Yes, please.
How does this measure compare with more traditional metrics like k-anonymity? Why did you have to come up with a new metric? Can you apply k-anonymity to this problem of information leakage?
Oh, right. So here I'm talking about the disinformation problem. I think your question refers to the measure of information leakage. So for k-anonymity, compared to k-anonymity, the k-anonymity measure is a 0 or 1 measure, where you're either completely safe or you're not safe at all. If there are, so your data is considered safe or not safe. It's a black and white thing. In comparison, for our information leakage measure, we can quantify more fine-grained notions of privacy. So that was about the measure, but this slide is more about how to generate disinformation records that can maximize the benefit of a target record. Oh, this is the budget we can you can use for generating the disinformation record. So there is a cost for creating a brand new record, right? And you can't simply generate whatever you want. So this is a way to kind of limit the total amount of information you can disinformation records you can produce using that will confuse the adversary.
So I have more of a problem with the benefit. How you quantify the benefit?
Yeah. So this is one way to do it. There are many ways to model this problem.
How do you come up with numbers about benefit?
Right. So one approach is to simply define the benefit as the number of records within this cluster. But that's not like the only way you can do it. You can, for example, compute the benefit by using an arbitrary function that works on like so after you merge the clusters, you can apply a general benefit function on all the records that have been mistakenly merged. But in this problem, we assume that you can somehow add these benefits by summing them together, and this makes the problem easy to solve analytically. So it's kind of we're not claiming that this is the only way you can define benefits, but this is actually an open problem that we haven't that has to be studied more. Yeah.
Isn't there some risk that someone might take this and use it in a different way to smear you?
Yeah. So these disinformation techniques can actually be very harmful for companies that are doing data analytics on big data. So in that case, if you're trying to extract profiles from social network, social media data, then
I was thinking along the lines of Obama really wasn't born in Hawaii; he was born in Kenya.
Okay. Yeah. So if people manage to So that's kind of misinformation. Here, I'm focusing on generating data that can confuse the adversary into thinking that different records refer to the same person or object. So it's in the same line as producing misinformation for President Obama. Yes.
It seems that, like, for this entire thing to work, we should have some notion of completeness of information. Right? In general, I don't know like what pieces of information about me are lying where. And without having this complete picture, how do I implement some some of these?
Yeah, this is a very case-by-case thing. So in general, you can't assume that you have knowledge of all your information out in the public. But there are some cases, certain applications where you do know where your information is. So a good example I always use is, let's say you're the camera company Nikon, and you want to, you kind of have your latest and greatest product, and you don't want to leak the specs of your camera. Now, there's a site called NikonRumors.com, which is dedicated to spreading rumors about the next best camera produced by Nikon. And people actually post rumors, information that they think is correct. And so, for example, you might guess that the next Nikon product is going to have 40 million pixels and has shutter speed of some few seconds. Have a certain shutter speed and so on. Now, you can also add a confidence value, which reflects how confident you are in this information. So there aren't too many rumor sites. So in this case, Nikon can sort of figure out where all its camera information is, where all the rumors of its camera are coming from. And plus, you might only be interested in these rumor sites as well. So the bottom line is, I'm not claiming that you have perfect information about all the data, but in real-world applications, for certain applications, it's enough to know you do have information about where your information is. You do have a good idea of where your information is located. I hope that answered your question. Okay. All right. So.
It seems to me like this strategy, when you get right down to it, this strategy is probably really for situations where other people are disseminating information about you. The kinds of information that you disseminate about yourself on places like Facebook and Twitter, and all these kinds of things, it seems to me like if you're putting it out there in the first place, the assumption is because you want people to know that about you. So would you say that it's correct to characterize that sort of the utility of this is really about spamming people who are trying to disseminate information about you that you don't want disseminated?
Yes, so I think you're getting at the issue of reputation. So you don't want to post information that gives a bad name to you. So this is
something about yourself that you don't want. You don't want people to know that or whatever. Like that's the camera example, right? I mean, you as a company, you don't want someone else to put the specs for your latest camera out there. So you go on a disinformation campaign to spam what people think they know.
Exactly, yeah.
But that probably doesn't apply so much to the things that you put out there yourself, because the assumption is if you put it out there, you put it out there because you want people to know. Is that a fair distinction to make?
Right. So here the problem is focused on trying to hide a certain information and lowering information leakage. It's not about trying to reveal information. Now there's an interesting startup called Reputation.com, which actually tries to solve the reverse problem, where they want to promote some of your positive information to the public. So they have these interesting web spam techniques where you can kind of make sure that some of your information appears in the top search results of Bing. Yeah.
I just wanted to keep an eye on the clock. Do you have enough time to cover here?
Yeah, I'll just move on. But these are all interesting questions, and this is a kind of an open problem. So in summary, I've proposed a new measure for quantifying information leakage, and I proposed disinformation techniques that can be used to reduce information leakage and thus manage it. So that was the second part of my talk. And for the related works, there's been a lot of previous works on anti-resolution and privacy. And instead of just listing all the works on one screen, I thought it would be a good idea to just talk about the high-level ideas. So there's been a lot of works on anti-resolution that focus on accuracy, and relatively few works that focus on scalability. MSR has been a pioneer in anti-resolution results, and I'm well aware of the data cleaning project by the DMX group, and I regularly cite papers from Surjit, Arvind, and Raghav. My work has been mostly focused on the scalability aspect of ER, and I've also proposed many new functionality for ER. So for example, my rule evolution work solves a new problem for ER where I want to update an ER result incrementally when the comparison rule changes frequently. For privacy, there's been a lot of data publishing works in the past. And again, most of these works assume that you somehow have complete control of your data, and there are anonymization techniques you can use to make this data set private before you release it to the public. In comparison, we assume that there's no such thing as perfect privacy, and we're just trying to be as private as possible. There's been a lot of measures on privacy as well. Again, just to address Ravi's comment, most of the measures assume that privacy is a 0 or 1 concept. And in comparison, our techniques assume that privacy can be anywhere between 0 and 1. So this kind of flexibility enables us to measure in a more fine-grained notions of privacy. And I am aware that MSR also has produced the state-of-the-art privacy measure called differential privacy from the Silicon Valley research lab. So for future work, I'm interested in many ideas. A direct extension of my work is to study data analytics in a more distributed setting. So you might end up performing data analytics on many machines, either because you simply have too much data to run on a single machine, or you might have privacy constraints where companies are not willing to share their information, so you're forced to run analytics from separate nodes. The issue here is to exploit parallelism as much as possible, and also performing analytics in an accurate fashion. I'm also interested in social networks. So nowadays you find a lot of graphs about people, and it's very important to analyze this information and identify interesting trends among people. So a few months ago, I got this email from LinkedIn, which is a professional social network, where they were telling me that they're solving this problem where they would like to resolve user profiles and user skills and companies so that they can connect users with certain skills to companies that want people with those skills. So in order to do this mapping correctly, you really need to resolve the people and skill sets and the companies correctly. And so you can immediately see that there are entity resolution problems here. Currently, I'm working on a fascinating topic called crowdsourcing, where the idea is to use the wisdom of the crowd to solve problems that are hard to solve using computer algorithms only. For example, you might want to resolve a set of photos where the goal is to figure out which photos refer to the same person. Now, if I show you 2 photos of Surjit, then you probably can immediately see that these 2 photos refer to the same person. But if you try to do this using a computer algorithm, this is going to be very challenging because this involves sophisticated image analysis. And even if you use those algorithms, the computer is probably not going to do a good job. So, the challenge is to ask humans just the right questions and use those answers to do the right clustering. Now, humans can be very slow, expensive, and error-prone. And so they make mistakes both intentionally and non-intentionally. So a significant challenge is to incorporate this erroneous behavior of humans when doing crowdsourcing. So in conclusion, data analytics is a critical problem. I've solved 2 problems within analytics, data integration and data privacy. And I've mentioned that there's an interesting connection between these 2 topics. The better you are in integration, the worse you are in privacy, and vice versa. So thanks for listening to my talk, and I'll open up to questions.
You got a lot of questions on the way.
Yes, this is fun. Thank you.